Module 3, Lecture A, Lists and Tuples. By the end of this lecture, you will be able to store sequences of engineering measurements in lists and access individual values correctly, use loops and built-in functions to summarize lists of mechanical test or operating data, and represent fixed grouped engineering values with tuples where appropriate. List operations. Indexing measurement lists. Indexing lets you retrieve a value from an ordered list by its position, which is useful for engineering data such as strain, temperature, or load measurements. In Python and many other languages, positions start at 0, so the first item is position 0, the second is position 1, and so on. With practice, this makes it easy to access the first, last, or any specific measurement without searching manually. Correct indexing means understanding both how measurements are taken and how they are stored. An index identifies a reading's position in a data list, not the measured value itself. For example, sensor readings stored in sequence may start at index 0, with later measurements at higher positions. To interpret an index correctly, engineers must also know the sampling rate and units so they can retrieve the right data and analyze events such as spikes or drops accurately. Accurate indexing is essential because choosing the wrong position can lead to incorrect engineering conclusions, such as reporting the wrong maximum displacement or comparing the wrong trial results. A common issue is an off-by-1 error, especially when zero-based indexing makes the 10th measurement appear at a different position than expected. Negative indices can be useful for accessing recent data from the end of a list, but the main goal is always to match the index to the intended measurement sequence. Python code. Indexing measurement lists. In Python, measurements can be stored in an ordered list where each value has a position. You use indices to select values by position, and negative indices count backward from the end of the list. We define a list to store pressure measurements in kilopascals. The values are in time order, so each position represents a reading taken at a specific moment. This makes the measurements easy to access and work with by their place in the sequence. Use the list length to count how many pressure measurements are stored. Then check that the count is exactly 5. An assertion raises an error if the number is unexpected, helping confirm the data has the right size before any indexing is done. Use list indexing to access specific pressure readings. The first reading is at index 0, the third reading is at index 2, and the last reading can be retrieved with a negative index of -1, which counts backward from the end of the list. To retrieve the fourth pressure measurement, first convert its position to Python's zero-based index by subtracting 1, giving an index of 3. Using that index on the pressure list selects the corresponding reading. This example shows how to access pressure readings stored in a list. It first displays the full list, then retrieves individual values using zero-based indexing, such as the first reading at index 0 and the third reading at index 2. It also shows that a negative index of -1 gets the final reading, and that a measurement number must be converted to its zero-based index, so the fourth measurement is accessed with index 3. This script shows how to retrieve values from a Python list of pressure readings in kilopascals. It checks that the list has 5 elements, then accesses readings using positive and negative positions, including the first, third, and last values. It also shows that the fourth measurement is found with index 3, reinforcing how zero-based indexing works in Python. Slicing lists. Slicing a list means selecting a continuous part of an ordered sequence. In engineering, it helps focus on specific time periods in data, such as temperature or pressure readings, while keeping the original order. This is useful because patterns and trends over a segment often matter more than individual values. When slicing a list, choose the start and end positions carefully, remembering that the end position is not included. Accurate boundaries help you isolate the right data, such as a specific phase in a mechanical test. If the slice includes too much or too little, it can change the results of your analysis. Slicing lets engineers work with specific parts of a data list while keeping the full dataset unchanged. This is useful for focusing on recent readings, calibration periods, or unusual behavior without losing context. When data is organized in a logical order, such as by time or location, slicing makes it easier to find key evidence and prepare results for further analysis or visualization. Python code, slicing lists. Organize pump temperature readings in order. Then select the intervals that represent useful operation. Compare the full set of measurements with these selected subsets to focus analysis on the most relevant data. We create an ordered list of Celsius temperature readings from a pump. Keeping the measurements in sequence lets us later extract useful subsets of the data for analysis. To focus on part of a temperature list, you can take a slice from index 1 up to index 5. This selects the 2nd through 5th readings, such as a warm-up interval, while leaving the original list unchanged. Use slicing with a negative starting position to get the last 3 temperature readings. This tells Python to count back from the end of the list and return the final 3 items without changing the original list. To review temperature data quickly, use slicing with a step of 2 to take every second reading. This samples the list by skipping every other value while leaving the original data unchanged.
First, print the full list of temperature readings to see the original data.
This gives you a baseline for comparing any slices or subsets and helps confirm that slicing does not change the original list. We print the warm-up slice to review temperature readings from the 2nd through 5th minute of the warm-up period. This focuses on the early rise in temperature, making it easier to examine how the system behaves during that initial interval. This step prints the last 3 temperature readings so you can quickly check the most recent data. Viewing these values helps reveal current trends or possible anomalies and makes it easier to compare recent readings with other parts of the dataset. The code displays every other temperature reading from a previously sliced list. This gives a shorter view of the data by skipping alternate entries, making the overall temperature trend easier to review quickly. After taking slices from the temperature list, we print the original list again to confirm it has not changed. This verifies data integrity and shows that slicing only creates extracted views or copies without altering the original sequence. This example shows how Python list slicing can extract useful parts of a temperature dataset without changing the original list. It selects a warm-up segment, the final 3 readings, and every second reading to give different views of the data. Printing these slices demonstrates how slicing helps analyze specific portions of a list efficiently. Accessing list values. Accessing values in a list means retrieving specific items from an ordered sequence, such as engineering measurements. Because the order often represents trials or events, choosing the correct position matters. In Python, indexing starts at 0, so the first item is at position 0. Knowing this helps prevent selection errors and supports accurate data interpretation. Accurate list access is important when data supports engineering calculations or decisions. Using the wrong position can lead to misreading measurements, such as pressure readings or fatigue test loads, and may distort the interpretation of a system or component. Always consider the list size to avoid accessing a position that does not exist, and connect each value's position with its physical meaning. In engineering, list values are often checked and compared to understand system behavior, such as changes in temperature or sensor readings under different conditions. Clear names and a consistent order help ensure each value matches the correct physical context. Understanding how a list is structured lets engineers connect data reliably to real-world observations and safety decisions. Python code. Accessing list values. Lists keep engineering measurements in order, and indexing lets you retrieve one specific measurement. In Python, list indexing starts at 0. We store 5 coolant temperature readings in Celsius as a list of floating point values. Keeping the readings in order makes them easy to access, compare, and analyze later in the code. Use the length function on the temperatures list to find how many readings it contains. This count helps you access list positions safely without going beyond the available elements. Specific temperature readings can be selected from a list using indexes. The first reading is accessed with index 0, the third with index 2, and the final reading with -1. These indexes make it easy to retrieve key measurements for comparison or analysis. The temperature rise is found by subtracting the initial temperature from the final temperature. This shows how much the coolant warmed during the recorded period. The program summarizes the coolant temperature readings by showing how many values are stored, then reporting key entries, the first, third, and final temperatures. It then finds the overall temperature rise by subtracting the initial reading from the final one, and presents the result rounded to 1 decimal place. We set the requested index to 3 to indicate which position in the temperature list we want to read. This prepares the program to check that the position is valid before retrieving the value. Before retrieving a temperature reading, the program checks that the requested position is within the list. If it is valid, it prints the temperature at that position in Celsius. If it is not valid, it reports that the index is outside the list, avoiding a runtime error. The script analyzes a list of coolant temperature readings by counting how many values it contains, retrieving the first, third, and final temperatures, and calculating the rise from start to finish. It also checks that a requested position is within the list before reading that value, which prevents unsafe access. When run, it reports these key temperatures, the total count, the temperature increase, and the requested reading if the position is valid. Data summaries. Mean values. The mean is a simple way to summarize engineering measurements with one representative value. It is found by adding all the measurements and dividing by the number of observations. This makes varied data, such as repeated strength or temperature readings, easier to compare and interpret, especially when small differences come from experimental error or sensor noise. Loops and built-in functions make it easy to calculate mean values from engineering measurements, even when datasets are large or vary in size. A loop can add repeated readings, such as forces or pressures, while built-in tools can quickly find the total and the number of values. This helps engineers summarize test data reliably, such as drag forces from a wind tunnel or motor current readings used to assess typical load demand. Mean values are useful summaries, but they can hide important variation in a dataset. In mechanical systems, outliers or brief extreme readings can make the average seem normal even when a problem occurred. Use the mean only after checking for missing data, sensor errors, and unusual values, and treat it as a starting point for further analysis with measures such as minimums, maximums, and ranges. Python code. Mean values. Mean values help summarize repeated engineering measurements, while lists keep related test readings organized. Built-in tools can then calculate totals and counts reliably. This means the code uses only Python's built-in features and does not need any extra packages installed. It keeps the setup simple and avoids external dependencies. We store 5 tensile strength measurements in megapascals as a list. This makes the engineering test data easy to work with later, such as when calculating averages or other basic statistics. Start by setting a running total for tensile strength measurements to 0. As each measurement is processed, add it to this total so the final sum can be used to calculate the mean. To find the total tensile strength, each measurement is added to a running sum. This ensures every value is included, creating the total needed to calculate the mean. Use the length function to count the tensile strength readings. This count gives the number of measurements, which is needed to calculate the mean by dividing the total strength by the number of readings. To find the mean tensile strength with a loop, add all the measurements to get a running total, then divide by the number of readings. This gives the average tensile strength for the list. To find the mean with built-in functions, add all the tensile strength readings using the sum function. Then divide by the number of readings in the list. This gives the average efficiently without manually looping through the values. The output first shows the tensile strength measurements and the total number of readings. It then reports the mean tensile strength found by a manual loop and by built-in tools, with both rounded to 1 decimal place. Finally, it compares the two results to confirm that the manual and built-in calculations agree. This script finds the average tensile strength from several measurements in megapascals. It compares a manual loop with Python's built-in mean calculation, and both give the same rounded result. By printing the readings, count, and matching averages, the script shows that the built-in approach is accurate and reliable for basic statistical calculations. Average values. Averages summarize mechanical test or operating data by turning many measurements into one representative value. They give a quick view of typical performance, though individual readings should still be checked for anomalies. An average is found by adding the values and dividing by how many there are, often using built-in functions for clarity and reliability. Loops can help filter or check data before the average is calculated. Averages are meaningful only when the data points are comparable and relevant to the question. Do not mix different kinds of measurements, and be careful that periods like startup or shutdown do not hide important patterns in stable operation. Use filtering or inspection to remove invalid readings and focus on the data that truly represents the situation. In short, averaging requires both calculation and context. Averages are useful, but they should be interpreted with other summaries such as range, minimum, and maximum values. The same average can hide large variation or brief unsafe conditions, such as inconsistent material strength or temperature spikes. Engineers combine built-in functions and flexible loops to calculate these measures efficiently and handle issues like sensor dropouts, making averages more reliable for comparing tests, monitoring systems, and reporting performance. Python code. Average values. Average values help summarize repeated measurements, while lists organize comparable engineering readings. Built-in tools make these summaries clearer and more reliable. A list is used to store repeated pump flow rate measurements in liters per minute. This keeps readings from different times organized so they can be analyzed later, such as calculating averages or filtering specific values. Use the length function on the flow rate list to find how many measurements it contains. This count is needed to calculate the average flow rate using the correct number of data points. The total flow rate is found by using the built-in sum function to add all flow rate measurements together. This cumulative value in liters per minute is then used to calculate the average flow rate. To find the average flow rate, first confirm that readings are available. Then divide the total flow by the number of readings, which avoids dividing by 0 and ensures the average is based on real measurements. A tuple is used to keep a pump flow label and its unit together as a fixed pair. It stores the description, pump flow, with the unit, liters per minute, so the program can consistently label and display flow data without those values changing. We begin by setting up a place to store stable flow measurements in liters per minute. This will hold only the readings taken after the startup phase, so later analysis focuses on more reliable data. To measure stable pump behavior, skip the first flow reading because it may be unreliable during startup. Use the remaining readings to form the stable flow set, so the average reflects normal pump operation. To find the average stable flow rate, add all readings from the stable period and divide by the number of readings. This focuses the calculation on data after startup, giving a representative average for steady operation. The output gives a compact summary of pump flow measurements in liters per minute. It shows the raw flow readings, then reports the overall average rounded to 2 decimal places. It also reports a stable average, rounded the same way, after excluding the initial fluctuations. This script summarizes pump flow measurements by first finding the average of all readings. It then removes the first reading, treating it as potentially unstable, and calculates a more reliable stable average from the remaining data. Both results are printed with clear labels, units, and values rounded to 2 decimal places, showing how filtering can improve engineering summaries. Range summary. A range summary shows the spread of a dataset by comparing its smallest and largest values and the difference between them. In mechanical data, it helps reveal whether a system is behaving consistently or showing unusual variation. For example, a large gap in tensile strengths from the same material batch may suggest defects or testing setup problems. In programming, lists can store the measurements, and built-in tools can quickly find the minimum and maximum values. Loops are useful for summarizing the range of large datasets by scanning values and tracking the lowest and highest readings. This helps check whether measurements such as pump pressure, brake temperature, or torque stayed within acceptable limits. Although a range does not show every detail, it gives a quick view of how much the values varied. A range summary should be interpreted with engineering judgment and an understanding of how the data was collected. A large range can point to unstable performance, but it may also come from sensor noise or a recording error. Engineers often compare range with the average, since 2 systems can have similar averages while one varies much more. In software and engineering analysis, range gives a quick check of variation and whether conditions appear stable and within limits. Python code, range summary. Range summaries show how spread out measurements are. Operating readings can be stored in lists. and loops can scan those lists to find the highest and lowest values. We store the pump pressure readings in pounds per square inch as a list. This prepares the data for later analysis of its range and variability. The code first checks whether the pressure readings list is empty. If there are no measurements, it raises a value error to stop processing. This prevents later operations from running without valid data. Start by setting the lowest and highest pressure values to the first pressure reading. This gives a valid baseline for comparing the rest of the readings and makes it possible to track the minimum and maximum pressures accurately. To find the lowest pressure, check each reading and compare it with the lowest value found so far. Whenever a smaller reading appears, replace the stored value with it. After all readings are checked, the stored value is the smallest pressure in the list. The code compares each pressure reading with the highest value found so far. When a reading is higher, it replaces the stored highest value. By the end of the loop, the stored value is the maximum pressure in the readings. Find the lowest and highest pressure readings. Then subtract the lowest from the highest to get the range. This range shows how spread out the readings are and helps describe their variability. Use Python's built-in minimum and maximum functions to find the lowest and highest pressure readings. Then find the pressure range by subtracting the lowest reading from the highest. This gives the needed summary efficiently without manually checking each value. A tuple is used to store the acceptable pressure range in PSI, with 45 as the lower limit and 52 as the upper limit. Because tuples cannot be changed accidentally, these limits provide a fixed reference for checking pressure readings later. To check whether pressure readings are acceptable, compare the lowest reading with the lower limit and the highest reading with the upper limit. If the minimum is not below the lower bound and the maximum is not above the upper bound, all readings are within range. The result is a true or false value showing whether the pressures meet the limits. The program reviews a list of pump pressure readings to find the lowest value, highest value, and overall range. It compares manual loop results with built-in minimum and maximum calculations as a quick check. It then displays the acceptable pressure limits and reports whether all readings fall within those operating boundaries. This script evaluates pump pressure readings by finding the lowest and highest values and using them to calculate the range. It handles an empty list as an error, compares a manual loop-based approach with built-in functions, and checks whether all readings stay within an acceptable pressure range. The printed output summarizes the readings, both range calculations, and whether the pressures meet the specified limits. Tuple uses. Tuple fundamentals. A tuple is an ordered collection of values like a list, but it is designed to stay unchanged after it is created. This makes it useful for compact structured data where each position has a fixed meaning, such as coordinates or dimensions. Tuples are best for representing stable facts whose values must remain in a specific order. Tuples are useful when data should stay fixed and be treated as one stable record. Unlike lists, they do not allow changes, which helps signal that values such as ordered dimensions should remain reliable during processing. This makes tuples a good choice for small records where both value order and stability are important. Use tuples when you need a small, fixed group of related values whose order is meaningful. Because tuple elements are accessed by position, each position should be clear from context or design. Tuples are best for stable data such as ranges, coordinates, or engineering settings that should be treated as one precise unit. Python code. Tuple fundamentals. Tuples are useful for grouping related engineering values into fixed records. Each position in a tuple has a specific meaning, which helps make programs clearer and easier to understand. A tuple can store a sensor's fixed location in meters using 3 coordinate values, 2.5, 1.2, and 0.8. Because tuples are immutable, this helps prevent accidental changes and protects the integrity of fixed engineering data. Tuple unpacking takes the sensor location tuple and assigns its 3 values to separate variables for the x, y, and z positions. This makes each coordinate easier to reference by name and helps keep later calculations more readable. The code displays a sensor location stored as 3 coordinates, then shows selected parts of that location. It first prints the full position, then the x-coordinate for the horizontal position, and finally, the elevation coordinate for the vertical position. This helps connect each tuple element to its meaning in meters. A tuple is used to store the fixed dimensions of a bearing in inches, its inner diameter, outer diameter, and width. Because tuples cannot be changed, this keeps these important values constant and helps prevent accidental modification. The bearing dimensions tuple is unpacked into separate values for inner diameter, outer diameter, and width, all measured in inches. Giving each measurement its own descriptive name makes later calculations easier to read and reduces confusion, which is especially important in precise engineering work. To find radial wall thickness, subtract the inner diameter from the outer diameter, then divide the result by 2. This gives the thickness of the bearing wall on one side. The code displays the bearing dimensions in inches, first as a complete tuple and then as separate values for inner diameter, outer diameter, and width. It then calculates the radial wall thickness by subtracting the inner diameter from the outer diameter, dividing the result by 2, and rounding to 3 decimal places. This final value gives the precise wall thickness needed for engineering calculations. This example shows that tuples in Python are immutable. When the program tries to change the first value in a tuple, Python raises a type error because tuple contents cannot be edited after creation. Catching and reporting that error confirms that the original tuple remains unchanged. Printing the message confirms that the sensor location tuple has not changed. This shows that tuples are immutable, meaning their elements cannot be modified after creation. Immutability helps protect data integrity by preventing accidental changes. This script shows how tuples store fixed engineering data clearly and safely. It uses tuples for a sensor location and bearing dimensions, unpacks their values, and calculates radial wall thickness from the inner and outer diameters. It then shows that trying to change a tuple causes a type error, confirming that tuples are immutable and useful for records that should not be modified. Fixed value groups. In engineering, tuples are useful for grouping related values that should stay fixed, such as a 3-dimensional point or a set of material properties. They show that the values belong together as one unit, rather than as a collection meant to change. This helps preserve important engineering data during program execution. In engineering software, tuples are useful for keeping related fixed values together as one meaningful unit. They preserve the order and integrity of attributes such as coordinates, ranges, or color intensities, making the data easier to interpret correctly. When paired with clear names and documentation, tuples help communicate that the grouped values belong together. Tuples are useful for grouping values that should stay fixed, such as constants, reference settings, or standardized properties. Because tuples are immutable, they help prevent accidental changes and make intentional updates more obvious. Using tuples for stable data and lists for data that may change improves clarity and reliability in analysis and control applications. Python code, fixed value groups. Tuples are used to group related engineering values when the group should stay fixed. Lists are better for data that may need to grow or change. A tuple is used to store the fixed x and y coordinates of a whole center in millimeters. Because tuples cannot be changed, this helps protect the coordinate values from accidental modification. The tuple, holding the whole center measurements, is unpacked into two separate values, one for the x position and one for the y position. This lets each coordinate be used individually, while the original tuple still represents the fixed pair of related values. A tuple is used to group fixed steel properties, density, elastic modulus, and yield strength. These values represent steel's mass per volume, stiffness, and the stress where plastic deformation begins. Storing them in a tuple keeps the related engineering constants together and unchanged. A tuple of steel properties is unpacked into separate values for density, elastic modulus, and yield strength. This separates the material's P properties, so each one can be used directly in later calculations or operations. A tuple can represent a bolt's fixed specifications in imperial units by grouping its diameter, threads per inch, and length. Because tuples keep related values together and unchanged, they help maintain consistency and clarity when working with fixed data. The prints check the stored center of a whole by first showing the full coordinate pair, then showing the separate x and y values. This confirms that the coordinates were unpacked in the correct order and represented accurately. The code displays key steel material properties in engineering-friendly units. It prints density in kilograms per cubic meter, elastic modulus in gigapascals, and yield strength in megapascals by applying the needed unit conversions. Use the length function to check that the bolt specification tuple has the expected fixed number of elements. Then retrieve the first item, which gives the bolt diameter in inches. This shows how tuples store fixed, ordered data and how individual values can be accessed by position. To update the coordinates, we create a new tuple with the values 36 and 18. This changes the stored position without modifying the original tuple, showing that tuples are immutable. Printing the new tuple confirms the updated center coordinates. This script shows how tuples can store fixed engineering data in a clear structure. It groups values such as a whole's center coordinates, steel properties, and bolt specifications, then separates those grouped values into individual variables for use. It also checks the number of bolt values and shows that changing a tuple actually creates a new tuple. The key idea is that tuples are immutable, making them useful for data that should stay constant. Tuple return values. Use a tuple when a computation produces several related results that should stay together. In engineering, this can include values from one analysis, such as strengths, strain, pressure, or efficiency. A tuple keeps these results grouped as a stable package, making them easier to pass through a program while preserving their relationship. Tuples are useful for returning related values whose meaning and order should stay clear and fixed. Unlike lists, which usually hold similar items, tuples often group different pieces of information from one result, such as measurements and a status indicator. This makes the returned data easier to interpret as one connected structure, rather than as separate or expandable items. Tuples can make engineering software more compact and expressive when a function returns a small set of related results. They work best when each position is clear from context or documentation, such as paired calibration or trajectory outputs. If there are many values or the meaning could be unclear, a more descriptive structure is usually better. Python code. Tuple return values. Tuples are useful for grouping a fixed set of related results. A function can return multiple values together, and unpacking lets you assign each returned value to a clear place. The summarize tensile test function takes a list of loads in kilonewtons and an area in square millimeters. It processes these values and returns 3 key results from a tensile test. This keeps the test summary logic organized and reusable. The code first checks whether the load measurements list is empty. If there is no data, the function returns a standard tuple containing 0 values and a no data message. This keeps the function's output consistent, even when there are no measurements to process. When the load list is empty, the function returns a standard 3-part result, 2 zeros and a no data message. This keeps the output consistent, so the caller always receives the same structure even when there is nothing to calculate. This step converts each load value from kilonewtons into a stress value in megapascals. Each load is first converted to newtons, then divided by the cross-sectional area in square millimeters, producing a new list of stresses. The code extracts 2 key stress values for engineering analysis: the maximum stress, which represents the material's ultimate tensile strength in megapascals, and the first stress value as an initial reference point. Together, these values help assess material performance and suitability for a given application. The diagnostic status is based on ultimate tensile strength. If the strength is at least 250, the material passes. Otherwise, it is marked for review. This gives a quick check of whether the material meets the required strength standard. The function returns 3 related results as one tuple: the ultimate tensile strength in megapascals, the first calculated stress value, and a status message showing whether the material passes or needs review. Grouping these outputs together makes the function's results easier to manage in a structured way. A list is used to store load measurements in kilonewtons from a tensile test. Keeping the values together makes it easy to process them later, such as converting loads to stresses or finding the maximum load. This helps analyze how the material responds under different loading conditions. A tuple is used to store 2 fixed specimen geometry values: the area 100 and the gauge length 95. Keeping these related measurements together makes them easy to use in later tensile test calculations, while the tuple keeps the data unchanged. The specimen geometry tuple is unpacked into 2 descriptive values: the cross-sectional area in square millimeters and the gauge length in millimeters. This makes the measurements easier to use in later calculations and helps keep the code clearer and more readable. The code runs a tensile test summary function using the load values and cross-sectional area. The function returns the ultimate tensile strength, the first stress value, and a diagnostic status, and these results are stored together for later inspection. The function returns 3 values, which are unpacked into separate variables for later use. These values represent the maximum stress, the initial stress, and a diagnostic status showing whether the material passes or needs review. The output first shows the full tuple returned by the function, including ultimate tensile strength, the first stress value, and the diagnostic status. It then prints the strength and first stress value in megapascals, rounded to 1 decimal place, followed by the status indicating whether the material passes or needs review. Finally, it checks the tuple length to confirm the returned output keeps a fixed structure. This script summarizes tensile test results by converting load values into stress using the specimen's cross-sectional area. It returns the ultimate tensile strength, the first stress value, and a status showing whether the result passes the 250 megapascal threshold or needs review. The example also shows how fixed-length tuples can neatly bundle related outputs and make the results easy to unpack and print. In this lecture, you learn to store sequences of engineering measurements in lists and access individual values correctly. Use loops and built-in functions to summarize lists of mechanical test or operating data. And represent fixed grouped engineering values with tuples where appropriate. In the next lecture, Lecture B, we will go over dictionaries and text.
Thank you for your attention. See you all in the next lecture.